Okay, quick recap. So lead this into part B of exercise 2 here. The common ion effect, remember the common ion effect is where you're adding or trying to dissolve a substance in something that already has one of those ions in solution. So common ion effect always affects the molar solubility by decreasing it. Why? Because, say for instance, in this example, the barium or the sulfate, if you add either one in, it shifts left towards the precipitate or the solid, therefore decreasing. Le Chatelier's principle will tell you it decreases the molar solubility. Same idea here if you're adding in product. Don't forget your Ksp, Ksp comparison. If you add in product, which would be one of the ions, you're adding to the numerator. So then Q is now greater than K, and that's why it would also, that directional pointing towards the precipitate occurs. Let's kind of recap on the common ion effect here. All right, for this one, we did all the calculations. We saw here this example, calcium chloride. The silver chloride was being dissolved in the solution that already had calcium chloride. Calcium chloride, of course, has 2 chloride ions per formula unit that's dissolved, so the common ion then would be the chloride. Now, I'm not going to redo the entire problem. But this type of problem where there is a common ion, you set up the Rice table. You have an initial concentration though because you have the common ion in solution. And then remember, after you set up the Rice table and everything, that the common ion concentration is usually way higher, way greater than the change is going to be. So you get to eliminate X, because it's not going to factor in. So you would take that X portion out of the overall concentration of the common ion part that gets inserted into the Ksp expression. So in that case, instead of doing adding in the X to the 8 times 10 to the minus 3, because we doubled that, you would eliminate X and you make your calculations go faster. So just recapping that, you can keep the X in and graph it, but that just takes longer. It's not going to really affect it. So this one, yes, it reduced our molar solubility to 2 times 10 to the minus 8, and that was a big difference than the regular molar solubility of silver chloride, which happened to be 1.3 times 10 to the minus 5. So adding it to calcium chloride reduced the molar solubility of your silver chloride compound. Now part B. Since we had a little bit of a recap here, hopefully this will seem pretty obvious to you. How do we calculate the solubility, the molar solubility of silver chloride in 100 milliliters of 4 times 10 to the minus 3 calcium nitrate solution? Where do I begin here? What should I start with? Well, before I even set up a Rice table, what should I have? Should have the reaction, right? Have the equation. So I'm going to start there. Here's I'm looking for the solubility here. AgCl. Going to give us Ag ions and chloride ions. All right. This is a 1-to-1, right? Molar ratio of ions being produced. So here, what else do I need to look at and consider before I begin? the calcium nitrate. Let's go ahead and take a look at that. Calcium nitrate. What is calcium nitrate? Well, calcium ions, nitrate ions. Okay, that 3 didn't come out very good. You fix that? This is going to break apart into these, calcium and nitrate ions. So, what does that mean for our overall problem here? What's the nuance? What's the little glitch here? No common ion, exactly right. So trying to trick you into doing something even though there's no common ion to be found. So how do we actually work this problem? We work it like it's a regular Ksp in pure water. So after the reaction, what comes next? We write out the what? Have our reaction, we write out our Ksp expression. So let's do that. Let's do the expression. Ksp equals the concentration of the silver times the concentration of the chloride. So then we just plug in, we get 1.6 times 10 to the minus 10 equals x squared. We square root, and the molar solubility is 1.3 times 10 to the minus 10 molar. Now, if you want to set up the rice table, you can. It's just not completely necessary because the silver chloride, we know, is 1-to-1 mole ratio. So the 1-to-1 mole ratios, what is the Ksp always going to be? Ksp equals x squared, because Ag and Cl are both going to change in the same amounts because it's 1-to-1. But what if it was a 1-to-2 or 2-to-1? What would the Ksp expression result in? If it was a 1-to-2 or 2-to-1 ion relationship, what does the Ksp equal always? To get the molar solubility. Yes, it's 4, well, it's 4x to the 4x to the third, exactly right. What if it was a 1-to-3 or 3-to-1? What is the Ksp always going to equal in terms of dissolving those ratio of ions? 27x to the fourth. And if it's a 2-to-3 or 3-to-2 ion ratio, what is it always going to be? 108 x to the fifth, exactly right. So those things are going to remain the same. I mean, we worked them out. We showed you how they came out to being those particular Ksp equivalents because of the concentration and then raising it to the power. So definitely go back and check that out if you're, like I know it's been a while because spring break and all, but go back and check those out because those are necessary for Ksp problems, following those ratios. All right, let's talk about QK problems in terms of solubility product. And I guess technically we should call these QSPs. Doesn't really matter. Okay. We are comparing K with Q now because we're going to start with initial concentrations. And we're going to see if it will precipitate. We're going to mix two solutions of ions together. and see what's going to happen. We're going to predict what will happen. And through the mathematical calculations, if Ksp equals Ksp, you're already at equilibrium. Okay, it's already saturated. Remember, that's the amount that can dissolve in the solution at the equilibrium state when it's considered saturated, that saturation point. However, you take these two initial beakers of ions, you dump them together in a new beaker, you calculate the initial concentrations of each ion that could form a precipitate. If Ksp is less than Qsp, that means you have more product, because the Q is higher, so it would shift left. And yes, you would end up having precipitate. This way, remember, that way left, forming the solid. And it will keep forming solid until it gets to the Qsp, Ksp is equivalent. Now, the third possibility here. Ksp is greater than Qsp, the last one right here. What does that truly mean? That means you ended up having less product, so it can dissolve more solid. We would consider this point not at equilibrium because it is technically unsaturated if more can still dissolve. So that third point is really telling you you can add more and it will still dissolve because you're in the unsaturated domain. So more can be added to get to that saturation point if Ksp is greater than Qsp, because it could go right and this direction and add more of the ions into solution and dissolve more. Now there's really only like one type of problem for these. So let me show you that one. It's long, but it's really not too difficult if you think about what is actually going on. Well, anything that's a K is going to be the equilibrium constant. So this is the equilibrium constant for substances dissolving in solution. Q, of course, is a reference point. You use the Ksp expression to find Q, but it is not the equilibrium concentrations you plug in. You would be plugging in the initial concentrations for Q, or the disturbed concentrations if you were disturbing an equilibrium. So remember, Q is talking about when it's not at equilibrium, Ksp is talking about when it's at equilibrium. Q is a reference point to see which way it's going to shift. Does that make sense? Different values using the same expression. All right, so let's take a look at this problem here. We have silver phosphate, Ksp for silver phosphate, room temperature right here. Would a precipitate form if 20 milliliters, 0.02 m AgNO3, silver nitrate, was mixed with 80 milliliters of 0.003 molar of sodium phosphate. So let's kind of set this up and get the visual here of what's going on before we dive into the Ksp calculations. We have two beakers here. We have the silver nitrate beaker. And in there, there's silver ions and there are nitrate ions. They are floating around in there because silver nitrate is soluble, because all nitrates are soluble according to solubility rules. So super large Ksp, we don't really care about Ksp for this one because it's totally soluble. But we have a beaker that contains 20 milliliters and it's at 0.020 M. Now we have another beaker here, like so. This one's going to contain our sodium phosphate. Now we have sodium phosphate, and I'm just drawing it in terms of the proportion of ions. Okay, so there's 3 sodiums for every 1 phosphate in there. So we have a solution there that is 80 milliliters and 0.003 molar. Ultimately, what's going to happen is these two are going to be dumped into a new beaker together, like so. And we're going to combine all those ions in there. Now remember too about the sodium phosphate. Sodium happens to be an alkali metal. Alkali metals are always soluble on the solubility rules. So both of those two initial beakers are completely soluble ions, large KSPs. Don't even worry about KSP because it definitely dissolves to 0.1 molar concentration, at room temperature, and probably greater than 0.1. So we're going to dump them together though, and we already know pretty much which one would precipitate if it does. We're not sure if it does yet because they told us at the top of the problem here, we've got silver phosphate and we have a KSP of 1.8 times 10 to the minus 18. So that's really the equation we're looking for here and we're concentrating on. Silver phosphate dissolving, we would get 3 silver ions out of that, and we would get 1 phosphate ion out of it, and we have the KSP value. Now, once again, nitrate's always soluble, and alkali metals are always soluble. So technically, the nitrate and the sodium are just spectators. They're not going to participate in any reaction here. So you can pretty much not even focus on those because they're just spectating. They're not going to participate in the reaction. If precipitate forms, it's going to form between the silver and the phosphate. We're not sure if it is because we have to find the concentration now. But when we take our 20 milliliters of the silver with our 80 milliliters of our phosphate and dump them together now in the same beaker, what happens to our volume? What happens to our lovely volume now? We've taken them both, dumped them together. It is now 100 milliliters. Yes, we have a new volume. So we have the new volume because we put them together. So 20 plus the 80. Well, now we have 100 milliliters. And we know when we get new volumes, what happens to our concentrations? They do change. They are not what they once were. Exactly, the concentrations will change. So our initial concentration here of our silver, because this is the one we're focusing on, was 0.02. But now that we've dumped it in with 100 total, we have to figure out that new initial molarity. How do we do that if we have a volume, a molarity, and another volume? What equation do we need to use? Yes, M1V1 equals M2V2. So that's what we're going to do here. We're going to start here with our first beaker, our silver. M1V1 equals M2V2. And we're going to calculate its initial concentration in the new volume. So we have 0.020 molar times the 20. And we're going to get the M2 times the 100. Like so. So the molarity here for is actually molarity 2 is going to be the concentration of the silver. Initially. I guess I should put an initial there. With the I. So what is the initial concentration of our silver then? 0.0040. Is that correct? Yay, okay. So that's our silver now. We have that checked. Okay, now we need to focus on the phosphate part. Whereas we started with 80 of that, 0.0030 molar. But now we have to figure it out of 100. So we also have to do, this is for the phosphate over here, M1V1 2B2. And this is times the 80. That equals M2 times 100. Like so. So M2 now, on this side, is going to be the concentration of our phosphate. And what is that going to be initially? Look at your eye. Yes, exactly right. Okay, so now that we have our initial concentrations, and we have our reaction or equation up here, we can use it to find Qsp. So Qsp is going to be equivalent to, or the expression, the concentration of the silver to the third times the concentration of the phosphate. And initially, the initial ones. So now we just plug them in and get our Qsp. So we have 0.0040 cubed times the 0.0024. So what do we get for our Qsp? Yes, 1.5 times 10 to the minus 10 is correct. Now, Ksp is up here. So we have the 1.8 times 10 to the minus 18 equals Ksp. And then over here we know Qsp is equal to 1.5 times 10 to the minus 10. Well, guess what? Qsp is greater than Ksp. Or Ksp is less than Qsp. So, will a precipitate form? Following the direction of the arrow. That is a yes. Exactly right. Remember, this direction means the solid's going to form. Yes. Precipitation occurs. Yes, it does. Now, if it was reversed, where the Ksp was larger than the Qsp, then you could still dissolve more. It would be in an unsaturated state. Yes, long problem. Not particularly difficult, but you do have to remember the whole new volume thing and recalculate those initial concentrations before you start. Sorry, what?
Forgot the ratios.
What ratios?
The ones we learned on the last page.
Well, here we wouldn't use those ratios necessarily because we have figured out the actual initial concentrations. We're not calculating molar solubility. We're calculating the initials to do Qsp. So yeah. Anyhow, This is the only type of QK type problem you'll see here in terms of solution equilibrium. I love how it takes my board a little bit while to process. There we go. And yes, precipitation occurs. Now we're going to talk about some factors that are affecting solubility. And this one might seem a little confusing, but do try to follow the logic, and we will hit on it a little bit more when we get to Unit 8, because then we will really get into, like, how is it a basic ion? What is a basic anion? And really, by definition, it is the conjugate bases of weak acids are always going to be basic anions. What does that mean? It means it will react with water and produce hydroxide, a little bit of it. So, solubility of compounds containing basic anions, conjugate bases of weak acids, increases as the solution becomes more acidic. So as the pH drops, where you're adding in more hydrogen ions, you're going to increase solubility of certain salts that have basic anions. Now here, we will go through in detail, like I said, in acids and bases of how to identify the basic anions, but we just look at these two examples here in the pictures. We are comparing a weak acid to a strong acid, basically. This is a weak acid, HF, hydrofluoric, okay, the weak acid. So that means fluoride, which would be part of the PbF2. Fluoride is a basic anion. It is a conjugate base of a weak acid. So this is why it works this way. Lower pH, where you have the free hydrogen ions floating around, because by definition, if the pH is below 7, you have more concentration of hydrogen. What's going to happen is a secondary reaction. The F is going to be removed and react with the H+. F, of course, being a conjugate base of a weak acid, is going to have a high affinity for those hydrogens, and it's going to form a bond, and it's going to create hydrofluoric acid. Now remember, weak acids are defined as weak acids because they only partially dissociate at a very minimal amount. Most of it stays as HF. Most of it does not separate. So if you have free F minus floating around, or fluoride floating around, and some hydrogen in there, well, the hydrogens are going to form a bond, therefore removing the fluoride from the solution. So if you have a salt like lead 2 fluoride here that dissolves and produces a little bit of fluoride, but you have free hydrogens binding up that fluoride, that's going to push this way, because essentially you're removing this. And according to Le Chatelier's principle, if you remove product, you create more product. So more would dissolve. So that's why you see in this diagram more of the little crystalline lattice structure is dissolving, because those fluorides are being taken away and bound up by the hydrogens and creating hydrofluoric acid. The diagram over to the right doesn't work the same way, because here you're talking about lead to iodide, and iodide is the conjugate base of the strong acid hydroiodic acid. So hydroiodic acid is one of the strong ones. Remember, it's hydrobromic, hydrochloric, hydroiodic, perchloric, chloric, sulfuric, and nitric. So 7 strong. So hydroiodic, when it dissociates, it completely dissociates, like 100%. So you get H plus and you get I minus. There is no affinity for wanting to bind with the H there. So the I's just kind of float around, the H's just float around. There is no reaction between them. Because it's strong, it completely dissociates, and that's why the solubility of that salt, the PbI2, does not increase, because it is not going to have a conjugate base of a weak acid. It has the conjugate base of a strong acid. Like I said, we'll hit that more later. What you should focus on here is the idea that conjugate bases of weak acids, which is everything but those 7 strong that I just talked about, those ones, if you put it in an acidic solution where you drop the pH, it will increase the solubility, as the H will bind with the conjugate base, and then you'll remove the conjugate base from solution and it will keep dissolving. That's one thing of how pH affects solubility. The next one is if you have a very insoluble hydroxide like aluminum hydroxide. Remember, most hydroxides are insoluble. The only ones that are soluble are the alkali metals, and calcium, strontium, barium have slightly soluble. They are considered strong because they have, when they do partially dissociate, you do have a higher concentration of the hydroxide. But aluminum hydroxide has like a Ksp of 10 to the minus 33 or something, really, really small Ksp. So therefore, it's a very insoluble hydroxide. It is also going to increase the solubility of an insoluble hydroxide if you make the solution acidic. So for this example, if we're looking at our aluminum hydroxide here, will it increase, decrease, or remain the same when dissolved in a solution with a pH of 3? Well, pH of 3 is an acidic solution. So the answer to that is increases. Now let's explain why. What are the H pluses going to react with in that equation? What are the H pluses going to react with there? The OH, exactly right. Because what does H plus and OH do? They form water. It's a neutralization reaction. So if you put aluminum hydroxide in an acidic solution, it will start removing the hydroxide by neutralization, which then again is like removing a product. And you remove product, once again, removing product, P over R, removing product makes that number get smaller. So Qsp would be less than Ksp. And it would shift, of course, to the right and dissolve more stuff. So definitely in there with Le Chatelier principle. So overall underlying concept. If it's an acidic solution, it usually increases the solubility of insoluble salts. For the most part, like I said, there's the few examples of the strong acid, ones that this would not affect. Insoluble hydroxides, conjugate bases of weak acids, okay? If the salt has a conjugate base of a weak acid, then it's definitely going to increase the solubility. Now let's talk about complex ions. You saw some complex ions in the lab. It was the cobalt complex with the water, that was the pink side, and then you had the cobalt complex with the chlorine that made it blue. So, sometimes they can give you a reaction with complex ions in there. And they tell us, of course, we don't really have to teach it, but you're supposed to still be able to apply the equilibrium concepts to any type of reaction. So they might give you one with complex ions. And complex ions usually are very colorful ions. A lot of them have color. So then they can be measured using spectroscopy because they'll have absorbance values, and then they can have you do Beer's law with it and other stuff along with the Ksp stuff. So I wanted to talk a little bit about complex ions. So if you see one in a reaction, you don't freak out and go, what the heck is that? I've never seen any chemical species like that before. Well, as you see here on this list, table of complex ions, now instead of calling it Ksp or Ka or Kb or Kc, they call it Kf for a complex ion. Kf because it's for the formation of the complex ion. Now, what you'll also notice too is looking at their Kf values, a lot of them are large, like this one, where the iron's combining with the cyanides, this one, the chromium's combining with the hydroxides, 10 to the 28th, or 29th, 10 to the 35th. Very large KXPs. So if they were to ever phrase it like, to what extent, looking at the extent of K here, if they say something like that, looking at the extent of K, and you see that K is super large, you're supposed to assume it goes to completion. And you're supposed to just do regular stoichiometry, no Rice tables, no equilibrium math. It would go just regular stoich math. So a lot of these complex ions really have a strong affinity. That means they bond up really quickly and they go to completion. The other thing you'll notice about these equilibrium reactions, the ions are on the left side, the complex ion or the group is on the right side. A little bit different than the solid is usually on the left and the ions are usually on the right. So that's something else that's a little bit different. And from the lab, if you already did your research and stuff and turned it in, like the metal ions, they act as Lewis acids, which is another definition for acids where it's an electron pair acceptor. And they form complex ions with Lewis bases, which are electron pair donors. That is the third definition of acids and bases. The first one's the Arrhenius, forms hydroxide and hydrogen and water. Second one is the Bronsted-Lowry, where you have the proton donor, proton acceptor type of definition. But here, Lewis, now it's reversed. The electron pair acceptor is the acid. The electron pair donor is going to be the base.
Are those only 3 we're going to have this year, or are there more?
What?
Is there more for definition-wise, or is it just those 3?
No, it's just those 3, yes. Just those 3 definitions. All right. So, basically, the formation of complex ions in solution increases the solubility of an insoluble salt. And let's really think about this in terms of Le Chatelier's principle. It's kind of a simple idea here. If you have the silver chloride, I'm going to write it bigger because you can't see it very well, plus the ammonia, and it forms the ammonium, or the silver ammonia complex, and some chloride here. So what happens here, basically, if you're looking at the first diagram, this is just the silver chloride in the water. And as you can see, it doesn't dissociate much because it's got a small Ksp. There's not many ions in there. However, you add the ammonia, these are the ammonia, they are binding up the silvers. These ones, they're taking the silvers out of the lattice structure. So what is it doing? It's dissolving now. It's increasing the molar solubility. And therefore, you end up with the complex ion. You have some ammonia and then you have some chloride. That particular case, because there's excess ammonia in there. So very soluble silver complex ion removes the silver ion from solution, shifts equilibrium to the right. Therefore, it's going to increase the overall solubility of our silver chloride salt. So complex ion formation increases the solubility of an insoluble salt. Now, exercise 5. Exercise 5 looks very intimidating. It looks a little crazy. You've got all those chemical species up there. You've got Ksp, you've got Kf. But really, exercise 5 is a regular equilibrium problem. It just looks like a big mess up there. And like, wow, how am I supposed to process all of that? Well, we process it and realize, since they gave us Ksp, Kf, we're really dealing with an equilibrium situation here. And if we just apply our regular equilibrium rules, we should be fine. So we're going to start with A here, calculating the molar solubility of silver bromide in pure water. Let's go ahead and do that. So this is just a regular Ksp problem. So we need our reaction. We have our reaction here. Dissolving it in pure water. We have our Ksp here, like so. Now, all we have to do is plug it in and do the expression, write out your expression, Ksp equals the silver times the bromide. So yeah, write out your Ksp expression. This is a 1-to-1 ratio. So Ksp is going to equal x squared here. Then we plug in our number. Your Ksp is 5 times 10 to the minus 13. All you have to do is do the square root, and you'll get your molar solubility. So the square root of 5 times 10 to the minus 13, what's that going to give us? Anyone calculate? Yay! There we go. 7.1 times 10 to the minus 7. Molar. This is how much of the silver bromide can dissolve in pure water per liter. How many moles per liter it can dissolve. Because the ratio is 1-to-1, 1 silver for 1 bromide is always x squared. Because both of them, the change is going to be x. Because every time 1 silver bromide breaks apart, it's going to produce 1 silver ion, 1 bromide ion. So the change is always going to be the same for those two, so it's just x squared. Because this is like x times x. So therefore, 1-to-1 ratio, we know it's 1-to-1 ratio with ions, it's got to be the Ksp equals x squared. And there we have that. Now, this part looks very intimidating, but it's not. Basically, what do we have going on here? Calculate the equilibrium constant, K, for this overall reaction. And notice what they gave you up here. They gave you a series of reactions that have their own K values over here that you can use. Now, if we're trying to find an overall K for one reaction off of a series of smaller reactions, what are the things we are allowed to do in order to find it? If we flip a reaction, what happens to the K of that reaction? If we flip one, what happens to the K? We do the reciprocal or the inverse. Good. If we multiply it by a factor, what do we do to the K? Yes, raise it to the power of that factor, right? And then when you have your series all lined up, ready to cancel, just like it's like a Hess's law problem, what do you do with your K values to find the overall? Yes, you multiply, exactly right. Okay, so let's take a look here. Do we need to flip anything? Do we need to multiply through by anything? Because we're just trying to get silver bromide, ammonia, silver ammonia complex, and the bromide. Well, look here, nothing needs to be done because all we need to do is cancel our silvers, and luckily they're on either side of the reaction. The first step, it's in a product, and in the second step, it's in the second part of the series, it's in the reactant. So they just cancel out nicely. So we do end up not having to do much here. We have our overall. All we need to do with our Ksp and Kf is multiply them. So we multiply them, plug in the numbers, and we get our new K value. So definitely looks intimidating with all of the chemical species in the complex ion, but we're really just applying regular equilibrium concepts here. Getting our new K value, which is 8.5 times 10 to the minus 6. Now, next step, we need to determine the molar solubility of the silver bromide if it's in a 0.25 ammonia solution. So, hey, we're taking this and sticking it in a solution with ammonia. And the ammonia we know is going to react with the silver to form the complex. So really, this is just a regular equilibrium problem. What do we set up for regular equilibrium problems? To help organize everything. Rice tables, yay! Let's do that. Let's set up a rice table. So go ahead, set it up. Now you have to cross off the solid. The silver bromide gets crossed off because it's the solid that doesn't participate in equilibrium. Just as long as it's present, you have to have some in there. But the AQ, all of those, of course, would be calculated into the rice table. Now we know that both the products started initially when we're dumping the silver bromide in there are initially 0. So we know it's going to shift to the right. So we don't have to do a Q calculation here. It's going to go to the right. That means we're going to subtract 2x from the ammonia since its molar deal is a 2 there. That means it's going to add x to both the products because they're 1 to 1 over there. So we get our equilibrium concentrations. And they have a bunch of x's in there. So looking at this, you could graph it. But you want to write out your expression first. Now remember, the expression is still same regular equilibrium stuff. Product times product over reactants raised to the power of the coefficient. Just like regular equilibrium would be. So you write out that expression. And then you can plug in the equilibrium concentrations. And yes, you could graph it. You could do the Y1 here. This could be the Y2 if you want to. However, what are we going to realize about x? Is x going to be a large number? The k is like 8.5 what times 10 to the minus 6. So x isn't going to be a large number. So you could take the whole idea of, eliminate the x deal here if you want to, and just calculate. Now, of course, you would want to say that you're eliminating x because it's negligible or that it's so small. If you're writing, you need to, cross it out and say eliminate x, small number there. so they know why you're doing it. And then you could put it in your calculator and graph it, or you can just calculate it with the eliminate x idea. If you calculated it with the eliminate x, you would get 7.3 times 10 to the minus 4. If you calculated it with the graphing, you would get 7.2 times 10 to the minus 4 for x. Yes, go ahead. Well, that 2 times x factor is not going to change this number right here. It's going to be so small that it's not going to really affect the 0.25. So do we need to keep it in there then? No, not really. But you could graph it. You can do it that route if you want. It's faster to eliminate x because you know that x is going to be so small that it's not going to affect the overall calculation there. Now, one other comparison to look at real quick is what was it in pure water? What was the silver bromide in pure water? 7.1 times 10 to the minus 7. So if we're looking here and comparing it to what it is now, because x, bromide is x, the molar solubility of the bromide of the salt definitely increased. It went up. 7.2 times 10 to the minus 4 is a much larger number than 7.1 times 10 to the minus 7. So by reacting it and creating the complex ions, the silver bromide solubility did increase quite a bit. One more quick thing before we move on to kinetics. The rest of the fractional precipitation or selective precipitation calculations, you will not need to know for the AP exam. If you want to go through them through the PowerPoint or even watch the video from last year, you're welcome to do that, but I'm not going to cover it because it's not going to be on the exam. This question, this example would be the only one that you will see. And that is where most of the time, these kind of questions pop up in multiple choice, where they give you like a table of 3 or 4 different compounds with their KSPs. And what they usually will do is they will show you or give you KSPs of compounds that have the same ratio. So for example, consider an aqueous solution that contains initially barium ion and strontium ions. A solution of the potassium carbonate is slowly added. Which ion, barium or strontium, will precipitate first? The KSP of the barium carbonate, so it's telling you this is one of the possibilities. Barium carbonate is 5 times 10 to the minus 9. The KSP of the strontium carbonate is 9.3 times 10 to the minus 10. And what you'll notice here about both of these situations is this is a 1-to-1. This is a 1-to-1. Strontium's +2, carbonate's -2. So these guys have the same ratio of ions in solution. That means when it does have the same ratio of ions, you can directly compare the KSPs. So KSP of barium carbonate is 5 times 10 to the minus 9. Strontium carbonate is 9.3 times 10 to the minus 10. Which one is the smaller one? The strontium carbonate. So which one's going to precipitate first? Which one has the lower solubility ability? The strontium carbonate has the lower solubility. And that is an excellent question. This is exactly what you do when they are not 1-to-1 and you have to compare. You don't directly compare KSPs. You have to go in, do the expressions, calculate the molar solubilities, calculate the X. So say for instance they gave you one that's 1-to-2 and they gave you one that's 2 to 3. Well, you would actually do the KSP, this case would be 4x to the third, and this one, you would calculate it with the 108x to the fifth. Then you determine the x values for both, like so, which would be the molar solubility. And you would calculate the molar solubility. The one with the larger molar solubility would be more soluble. The one with less molar solubility would precipitate first. Now, I wouldn't suspect that you would see something like this in the multiple choice. They might give it to you in the free response, but I don't think that they would give you something that math heavy in the multiple choice section, where you couldn't directly compare. You would have to calculate molar solubility there. Good question. If it's not the same ratio of ions, you have to calculate molar solubility and then compare those values. So, strontium carbonate, since the KSP value is smaller, there you go.